Welcome to review our work. My name is Fang Liu. The title of our work is Deep Convolutional Neural Network and 3D Deformable Approach for Tissue Segmentation in Musculoskeletal Magnetic Resonance Imaging. Image segmentation is the fundamental image processing step in many MR studies. Manual segmentation is usually time-consuming, therefore fully automatic segmentation is favorable. The majority of recently proposed methods for fully automatic segmentation can be categorized into model-based and analysis-based approaches. Besides model-based and analysis-based approaches, other approaches have been proposed utilizing graph-based methods, machine learning-based methods, as well as the methods that hybrids and combine strategies from multiple approaches. Despite promising results by model-based and analysis-based approaches, both approaches rely on a prior knowledge of object shapes and require high computation cost and relatively long segmentation time. In addition, both approaches might perform poorly when there is the high subject variability and significant differences of local features. With the rapid advance of deep learning methods in recent years, there have been several successful applications of deep convolutional neural networks, CNN, based methods for medical image segmentation, including segmenting brain tumor, MS lesion, brain tissue, cardiovascular tissue, etc. Those networks are highly efficient. However, some of them are specific to particular image domain, therefore require extra effort for generalization. In this study, we introduced a combined CNN method using convolutional encoder-decoder CED and 3D deformable modeling for tissue segmentation. The CED network provides rapid and robust initial segmentation, while the 3D deformable modeling refines smooth and desirable tissue boundary. Our contribution is, firstly, we desired a fully automatic pipeline for tissue segmentation where no manual interaction is needed for desirable segmentation results. The technique is generalizable and amendable towards a broad range of image segmentation tasks, which could potentially be a fundamental core for other segmentation-based image analysis techniques. In addition, we test our methods on multiple musculoskeletal imaging datasets. The result is excellent and superior to most of the state-of-the-art methods. The key for the segmentation pipeline is the deep convolutional encoder-decoder network, which turns slice-by-slice image into pixel-wise tissue labels. Differing from other typical segmentation networks, the CED network typically features the paired encoder network and corresponding decoder network. There are a few recently proposed semantic segmentation CED networks with high segmentation efficiency and accuracy evaluated in a variety of computer vision applications. For example, the UNet and the SegNet. The following work is primarily built upon the SegNet and its variants. A basic element of encoder network consists of multiple processing layers. The convolution layers utilize a set of 2D convolution filters to extract spatial invariant, robust image features. Batch normalization layers is used to reduce the internal image covariance shift during training, thus can improve the training efficiency and accuracy. The rectified linear unit performs pixel-wise feature activation function. And finally, the polling layers is used to reduce image feature size by max polling. The basic combination is repeated several times to process the raw input image into compressed representative image features. The encoder is the essentially famous VGG16 network, originally proposed for large-scale image recognition tasks. The decoder network element is similar to that of the encoder network, except the polling layers is substituted by an unsample layers used to upsample image feature maps. With the few upsampling process, the high-resolution image features are generated. The final layer of the decoder network is the softmax layer, which produced pixel-wise class probabilities. To recap, CED network typically consists of an encoder network for image data compression and feature extraction, while corresponding decoder network is utilized to recover high-resolution image labels, typically through efficient upsampling process. The typical CED network uses 2D convolutional filters, which limits image features into a single 2D plane. This is likely suboptimal for segmenting 3D objects in MR images, especially for images with anisotropic voxel. To maintain overall object shape and refine smooth surface, we further propose to convert binary segmentation mask into 3D mesh and perform three-dimensional deformable modeling based upon image boundary gradients. We first take this output from CED network and convert it into 3D simplex mesh using machine cube algorithm. The image boundary is determined by using combined diffusion filter and recursive Gaussian filter. An iterative process is performed to adjust the mesh vertices following the Newtonian law of motion. After sufficient iteration, a stable solution should achieve, and 3D mesh converges into image boundaries. A successful 3D deformable model should help maintain a desirable smooth object surface. The full segmentation algorithm is summarized as follows. First, 3D image volume is disassembled as a stack of 2D images. In the training phase, CED deep learning network uses the batch of 2D image slices as input and compares them to the corresponding pixel-wise class labels in the training dataset. The categorical cross-entropy loss function is estimated for the image loss, and the network parameters are updated using stochastic gradient descent algorithm until the optimization reaches the predefined maximum iteration step. The result is selected based upon the iteration where the image loss is the lowest among all the iterations. The segmentation phase, however, uses the well-trained CEDs as the front-end classifier to segment test 2D image slices. 3D pixel-wise tissue labels from CED network are passed into individual 3D deformable process, where each image object is deformed based upon the image boundary gradient. The final 3D segmentation is generated by combining all the deformed objects. Here, we comparing the segmentation result from our methods and the ground truth from manual segmentation in a T1-weighted fat-suppressed Lee image. The image was acquired for a subject with severe Lee osteoarthritis and thin cartilage, posing challenges for automatic segmentation methods. Our method achieves high segmentation accuracy with high dice coefficient for segmenting femur, tibia, femoral cartilage, and tibial cartilage. In contrast to manual labeling, which takes hours, our methods only requires 3 minutes segmentation time per knee joint. We evaluate our methods on the online knee joint image dataset hosted by Mikai 2010 SKI-10 workshop. The network is trained on T1-weighted knee images from 60 subjects and evaluated on 40 subjects. A rank score was given based upon segmentation accuracy for bone and cartilage, with higher score the better performance. In contrast to other state-of-the-art segmentation methods, utilizing atlas-based, model-based, and hybriding approaches, our method achieves an overall score of 64.1, which put our method in the second top position. Our method using CED plus 3D deformable modeling achieves the top performance for femur segmentation and the second top performance for tibial, femoral cartilage, and tibial cartilage segmentation. Notice that our CNN-based method is also extremely time efficient, with negligible running time compared to other non-CNN methods. This example shows cartilage segmentation performed in a clinical patient imaged with the fat-suppressed 3D fast-spin echo FSC sequence, which has different tissue contrast than the fat-suppressed T1-weighted SBGR sequence used in the SKI-10 challenge. The proposed fully automatic method demonstrates good agreement with the manual segmented cartilage for femoral, tibial, and patella cartilage on the sagittal image slice. Please see more details in our paper for group-wise statistical results for cartilage morphological analysis. This example shows cartilage segmentation performed in a clinical patient imaged with the T2 mapping sequence. The top row in this image shows T2 maps from several selected sagittal slices from the joint. The middle and bottom rows demonstrate the segmented femoral, tibial, and patella cartilage from the T2 maps using the manual segmentation and the fully automatic segmentation methods representatively. There was no significant difference between segmentation methods for the T2 relaxation time for femoral cartilage, tibial cartilage, or patella cartilage. This indicates the fully automatic methods as proposed in this study can provide accurate and time-efficient cartilage T2 quantification, making it a very useful practical tool for large population-based knee osteoarthritis research studies. As the further extended application of our proposed methods, in another study for quantitative evaluation of pulmonary ventilation, we tested our methods on 3D radial ultra-short echo time images for segmenting and assessing lung volume. The CED network was trained on 24 subjects, including healthy subjects, patients with asthma, and patients with cystic fibrosis. The evaluation was performed with another 10 subjects. Our method achieved high segmentation accuracy with average 90% dice coefficient for segmenting lung volume, and also achieved high segmentation efficiency with average segmentation time less than 1 minute. As another extended application of our proposed method, we also evaluate our methods in brain imaging. In this retrospective study, the goal is to automatically segment bone, ear, and soft tissue from a T1-weighted T1 Bravo images. The complex structure and similarities between ear insidus and bone signal make this a challenging task for conventional model and atlas-based methods. For training, we generated the ground truth labels by using CT images from the dataset. We trained our network with 30 subjects and tested on another 10 subjects. The segmentation using our method is of high quality. The ear and soft tissue segmentation both have high dice coefficient above 90%, and the bone segmentation has 80% accuracy. To summarize current study, we provide a novel fully automatic pipeline using convolutional neural network and 3D deformable process for multiple tissue segmentation in medical imaging. Our method is rapid, accurate, and adaptive to various image domains. The result tested is excellent and superior to most of the state-of-the-art conventional methods. This technique, utilizing convolutional neural network and 3D deformable process, could potentially be a fundamental core for other rapid segmentation-based image techniques. I would like to thank your attention, and if you want to know more details, please check out our MRI paper entitled Deep Convolutional Neural Network and 3D Deformable Approach for Tissue Segmentation in Musculoskeletal Magnetic Resonance Imaging. Thank you.